What's wrong?
That way that they'd be able to communicate with each other with those IPs.
Why not? What did we say they needed to be on the previous slide? We said they needed to be in the same subnet, right? Are those IP addresses in the same network? No. One is a 10.1 and one is a 11.2, so it looks like somebody fat fingered it. They typed in an 11 instead of a 10 because the question told us that Atlanta is correct. So what's the most appropriate answer? That is correct. That's a subnetting question as well, but notice you didn't have to do any calculation, but you're supposed to know that those serial interfaces have to be in the same subnet. So you should be able to recognize by the IP address on both of those configs that that's what the problem is. Does that make sense?
Yeah.
So that just highlights the fact that you guys need to don't skip those Excel spreadsheets because that's what's going to develop your subnetting rhythm so that you can see how things are supposed to be and how they're not supposed to be. All right? Amas, have you get a chance to look at the Excel spreadsheets, the subnetting stuff and all yet? All right, let's go on to this one. A network administrator has subnetted the 172.16 network using a mask ending in 192. A duplicate IP address of 172.16.2.120 has accidentally been configured on a workstation in the network. The tech must assign this workstation a new IP address within that same subnet work. Which of the following 6 addresses should be assigned to the workstation? What is the key to everything? Block size, yes. How do we figure out block size? Step number 5, right? Is it 5 or 6? I can't remember. It's in blue underneath red. Block size equals what?
Yeah, a friend of mine now is block size equals 256.
No.
256 minus the mask and the offset equal firing bits.
Okay, so which portion of the subnet mask are we going to subtract from 256 in this example? We're actually drawing from 2 places because what class of address space is this? a class Bravo. So we're borrowing all 80 bits in the third octet, and we're borrowing 2 bits in the fourth. So if we subtract 192 from 256, if we subtract 255 from 256, we get a block size of 1 in the third octet. What's our block size in the fourth octet? $256 minus 192 is what? 64. Excellent. So if you notice the question, it says you've got to assign a workstation a new IP address within the same subnet. Same subnet is what? The same subnet as this guy. So the question then becomes, what subnet is this guy in, right? So how do you determine what the available subnets are, and more importantly, which subnet this guy is in? How do we figure out the valid subnets? Step number 5, right? What does it say? Start at
0.
Right, and increment by the
Block size up 2. And
right. Right. So the first valid one that matters, we don't need to increment by the 1 because we know that this is a 2 in the third octet. So it's going to be 2.0, 2.64, 2.128. What's the next one? 2. What's 64? 192, isn't it? Yeah, that's it. 192. So the question is, what subnet does this guy sit in, and how do we know? That's a true host IP. Go ahead. Let me ask this question. Wouldn't 2.120 go in between 2.64 and 2.128? Yeah. So if this is the network address, what's the first usable, assignable host IP in that subnet? Right. 65, 66, 67, 68, all the way up to 127. Actually, 126, because 127 is the broadcast address. So yes, 2.120 sits in the 2.64 subnet. So the question is, which one of these also sits in 2.64? Yeah. 2.80. That's it. But I walked you through that because that's the logic that you've got to do on your own to be able to get to that point. Does that make sense?
Yeah.
Which means if you don't feel like you're proficient, then you just have to do these types of questions more often, that's all.
Yeah, I'm writing down some more stuff to help me out that makes sense.
Right. All right, let's go back to something that you guys should be a little bit more familiar with. How many ever you made? On PC1, it takes PC2, what three things will the quick router do with the data that's received for PC1? And why is the machine going so slow?
Yeah, I did pretty like robotic.
Really? Hang on a minute. All right. Where's the packet now?
Oh, that sounds better.
All right.
So one of the things is something of C.
Yeah. Let me ask this question. Where's the PDU now?
What?
Mike, you out there? Hey, Fabio, look at the question. This is Fabio, this is the exact same question that we went over. Yes, Tuesday, I think. Same exact question. So make sure you understand the question that's being asked. The question tells you where the PDU is. Where is the PDU now?
So it's the router.
Yeah, it's at the core router. Where is it going?
It's going to PC. In the end, it should be going to PC2
Right. Where did it come from?
from the router.
Negative. Where did the PDU come from?
Oh,
It's sitting at the core.
right.
Where did it come from?
It came from PC1.
Yeah. Yeah, I'm not trying to trick you, man. It left PC1 PC1, it's sitting down at the core router, and it's going to end up at PC2. What's the source IP address in the frame as it resides at the core router?
The source is PC1.
What's the destination address, IP address?
PC2.
Correct. Does the source and destination IP ever change? Good. So as the PDU sits at the core router, getting ready to exit the fast Ethernet 1.0 interface on its way to PC2, what's the destination MAC address?
PC2.
Good. What's the source MAC address?
The core.
Be more specific.
Oh, the FA10.
Yes, it's the layer 2 MAC address of the fast Ethernet 1.0 interface on the core router. If you tell me who, I have no idea, because I see two interfaces there, so I don't know which layer 2 address you're talking about. So you've got to be specific. You're exactly correct. The issue is you're not comfortable in your response, which tells me that you just have to answer more of these questions. Make sense?
Yeah.
So that you get more confident because you know the answers. But you've got to follow that same flow. You know what I'm saying? You've got to go, hey, if PC1 is sending something to PC2, is PC2 in the same local area network? No. Then where does that frame have to go? Okay, it's got to go to the default gateway for PC1. What's the source and destination IP address that never changes? What's the source and destination MAC address that changes at every hop? If you follow that same process every single time, you'll be able to answer these with a high degree of confidence. Does that make sense? So now that you know that, tell me what the three answers are. You already chose Charlie. Charlie's one of them. Give me another answer.
Alpha?
Yep, Alpha's right. What's the last one?
F.
Foxtrot. There you go, man. Excellent. Excellent. There you go. You got it. So that, again, just tells me you've got to do more practice with answering some questions. And I'm going to show you today, we've got some free and paid resources that you can utilize to answer these types of questions so that you can be a little bit more comfortable and confident in your responses. Sound like a plan?
Yeah.
All right, good deal. What are some characteristics of talent? Come on, are you back or are you just hanging out here? I don't know if he's back here or not, maybe. We'll do this last question, and then we'll do something else, and maybe we'll answer some questions when Mark comes back or later on this afternoon. So just try this one.
From the top of my head, I know it's data in clear text.
Yep. Yeah, absolutely. Good. Excellent. 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 Good for you. All right, we'll answer some more questions when Mark comes back. I don't want you to be tasked with answering all the questions by yourself, all right? Sound all right? Or you want to answer some more? It's up to you, man.
I'll go ahead and wait a moment.
All right, no problem. Let's go ahead and get rid of these. Let me go ahead. Let's take 5 minutes, and then we'll come back and we'll do some content. Sound like a plan?
Yeah. Yeah.
All right, let's take 5. I'm back. You out there, Fabio? You back? Okay. You come back? I don't know what's going on with Ron. He must still be experiencing some issues.
Is he able to call in through his phone?
He should be able to call in through his phone, but it looks like he's logged in.
Hi, I'm back. I just connect with my phone, so I follow with the technicians now doing. I just log in with my phone.
Oh, you log in with your phone so you can listen in. All right, great.
Yeah, I'm listening. I'm following my technician with me.
I gotcha. Are you at home or at your office?
No, it's home.
Oh, okay. Gotcha.
Yeah.
I hear you. All right, man. I'm just going to keep going then if it's all right with you. All right, I'm going to finish up this part on automation with configuration management, which is really the changes in a software application with respects to its requirements, its functionality, and the overall management approaches. And we're going to talk about both of them and some of the tools that are available to software developers out there. These are the guys that you and Amat are going to have to support in the future. There's a pull model where hosts a push model where you have a server that pushes the configuration down to the hosts. Now, we're going to talk about three tools: Puppet, Chef, and Ansible. And they represent different ways to achieve a common goal of managing a large-scale server infrastructure. So we're going to talk about some of the specifics of those tools over the next few minutes. Now, knowing where to get started with automation can be a daunting prospect for most IT groups. One of the first considerations is going to get an organization to ask which automation tool to use. And there's a number of different tools that basically fall into one of two camps, either agent-based or agentless-based. So you ask, what is an agent? Agent-based tools, like Puppet, require the user to install a piece of code on each device that you're going to manage called an agent. The disadvantage of this agent-based approach is that there's a reduction in flexibility if you just have to go in and make a quick change to just a small number of machines. How about the agentless-based tools? Well, tools like Puppet, Bolt, and Ansible don't require agents to be installed on the machines, which is great when you just need to make a quick change or deploy a machine without the added effort of creating a configuration template for the master to be able to manage it. The real benefits are realized when tools with both agent and agentless capabilities are out there to complement each other, such as with Puppet Enterprise or Puppet Bolt. So we're going to talk about a couple of these. Let's look at Puppet first. Puppet is a software configuration management tool that's mainly used by system administrators and cloud admins. It helps declare the system configuration and then be able to apply it across a lot of systems at a time. We're talking about hundreds or tens of hundreds or even thousands of machines at a time. It's an open source configuration management solution that's built on Ruby, and it offers some custom domain-specific language and embedded Ruby templates. It gives you an automated way of delivering, operating, and future-proofing all of your infrastructure and software devices. And it can run on any Ruby installed platform like Microsoft Windows Server, Linux, or Oracle Enterprise. Here are some of the components that make up Puppet. You've got a Puppet Master, Puppet Agents, a configuration repository, facts. Facts are the details related to the host or the master machine that's used for analyzing the status of any of the host devices that it manages. So changes on any one machine is based on what we call facts. And then there's a catalog. So all manifest files or configurations are first converted into a compiled format called the catalog. And then these catalogs are then applied on the target machines. Chef is a configuration management technology that's developed also on Ruby, and it's used to automate the provisioning of your infrastructure devices. You can integrate it with any cloud-based platform like Azure or SoftLayer or Rackspace to configure a new machine. And it supports Ubuntu, Linux flavors, Solaris, AIX, anything of that nature.
Yeah, there's nothing here. Oh, nothing, right? Yeah. So if I want to change the router from down to, from up to down, so
here are some of the components that make up Chef. You've got a Chef node, which is any machine that you're going to manage. Why did I have that up there? Oh, okay, sorry. A workstation is a PC where the Chef development kit is run to author cookbooks, kind of cute, right? Knife is a Chef command line tool. You've got a repository structure which holds the cookbooks that you author. And a cookbook is the configuration and policy that defines and supports a specific scenario.
Done now?
In some of the areas where you use Chef, which is application deployment, infrastructure configuration, and network configuration management. Ansible is a simple open source IT engine that automates application deployment, cloud provisioning, and some other attributes. And compared with Puppet and Chef, Ansible was developed to simplify the orchestration and configuration management tasks. It's written in Python, and it allows users to script commands in YAML. Here are some of the components that make up Ansible. So any machine with an installed Ansible can act as a control node. Managed nodes are those hosts that you see here on this slide. An inventory is a file that contains a list of managed nodes. The unit of code that's executed by Ansible is known as a module, and then the unit of action or activity inside of Ansible is called a task. And again, this is another tool that helps IT organizations provision with the additional assistance of configuration management, deploying apps. You can also do some reporting and things of that nature. And oh, by the way, it's agentless. So after you connect the host devices that you're going to manage, Ansible will push down the programs called modules. Those modules are then run and then removed when they're done.
Well, you want to try to make
now, I mentioned IBN, right? Intent-based networking. We're going to talk in a little bit more detail. But what is intent-based networking as a review? Well, IBN is an emerging technology that aims to apply a deep level of intelligence and intended state insights to networking, with the thought process that it's going to replace the manual processes that we do today with regard to configuring our networks and reacting to different issues with our networks. So simply put, administrators like you and I can send a request to tell the network what outcome we want. That's the intent, instead of needing to code and execute individual tasks in a manual fashion. So what's the purpose of intent-based networking? Well, the purpose primarily is networking that uses machine learning and cognitive computing to allow for more automation so that there's less time spent on manually configuration and management tasks. So with an intent-based networking solution, you and I can define an outcome or a business objective, the intent, what we want, and then the network software figures out how to achieve that goal or that intent thanks to artificial intelligence and machine learning. All of which is designed to automate the different tasks that we do manually today and to provide real-time visibility into the network's activity. So to predict proactively how we can troubleshoot and things of that nature. So how does intent-based networking work? Well, we said that it relies on AI and machine learning to perform routine tasks, to set policies, respond to system events, and to verify the goals and objectives. So, for example, if it can make servers reachable from specific networks, if that's what's required, it not only configures network changes, but also verifies that they're being performed, and you can make adjustments as required. And we have our own IDN solution called the Cisco Digital Network Architecture. That's a central platform, and it's our bridge to intent-based networking. It's used by medium and large companies to manage their operations on a single dashboard. So by reviewing or viewing all of your network components in one platform, it helps to improve not only performance, but it makes it more secure, and you can respond to issues that come up in a more timely fashion. It's a complete management console that's designed, created, and implemented by Cisco. It is a platform that includes tools for network management, network automation, visualization, analytics, and assurance. You can also incorporate the Internet of Things and security. And up until now, you would have had to buy multiple third-party tools to basically bolt onto your network. Now you can have a single dashboard that we're going to see here. Here is a single Cisco DNA Center appliance that controls all of your devices, both your physical as well as your virtual. So you've got a design module here, and then you've got the ability to collect information and create a policy. So you can take all of the status information about all of your network devices that are out there. You can translate that into a specific device configuration file based on different types, different makes, different models, different operating systems, etc. And then once you've created your policies inside of Cisco DNA Center, provisioning is a simple drag and drop task. So you can provision your devices remotely by one guy sitting there just dragging and dropping the policy-based configuration files onto whatever equipment you want to bring up. And then there's an assurance that provides a way to ensure that you are keeping up with your service level agreements to meet the business demands of your customers that you support. So it has a way of proactive and predictively anticipating problems or issues so that you can troubleshoot proactively. Here are some components that make up the Cisco DNA Center. You've got a discovery tool that can scan the network for new devices. There's also an inventory tool that you can import that new device information to. You've got a topology tool that helps you create a physical and logical topology of the inventory. You've got an image repository tool. There's a command runner tool that you can use to bang your CLI commands against your devices. There's a license manager tool as well. So you've got everything that you need from a single location. You can also perform a path trace between two devices, specifying the source and destination. And so it collects topology data and routing information from your devices. So if you look here closely, it'll show you the protocol of the device along with the other devices in the path. And that's about it, gentlemen, for this. Any questions at all about any of that stuff?
No, but it was all pretty cool.
Gotcha. All right, now we're going to talk about OSPF. Anybody have any experience with OSPF?
No.
The data is limit of data when off.
I mean, I think that does happen, but I mean, you have to be using a lot of internet for that to happen. I mean, that wouldn't cause a problem.
Okay, you can replace and put in my account.
So before I did it, I was just letting you know, if we do that, we could, because it looks like, are you connected right now? Because it looks like it's finally booted back up.
No. Not here. Try this one.
All right. So the objective of a dynamic routing protocol is to be able to exchange information between routers and to be able to respond to changes in the network. So if you have a interface that comes up or goes down, your dynamic routing protocol should be able to respond to those changes automatically to make changes about the routes that are installed in the routing table. So see how we're building on that question that a router answers when it receives a packet on an interface? And we've talked already about routes that get in there as a directly connected route automatically. And then yesterday we talked about static routes that are inserted into the routing table by somebody with privileges like you and I. You guys got a little exposure to that. Today we're going to talk about the third way that routes get installed in the routing table is through the use of a dynamic routing protocol. So as a networking engineer, you're going to encounter different routing protocols when you define, configure, and you troubleshoot your networks. And if the protocol that's being used is OSPF, you're going to need to understand different aspects of OPS. You need to understand how it functions. You need to have some familiarity with the different packet types that get exchanged, how the link state database gets built, how does routers that have been configured for OSPF establish a neighbor relationship with directly connected neighbors, something that I'll refer to over the next few minutes as neighborship. You'll also have to be able to configure and verify different OSPF configurations. So that's what we're going to talk about. One of the things that I want to include, however, in this discussion is where OSPF sits under the umbrella of dynamic routing protocols or protocols in general. So let's talk about this for a minute. A dynamic routing protocol is used to discover remote networks, maintain up-to-date routing information, choose the best path to a destination network, and then find a new best path if the current path is no longer available. So that's the overall idea around a dynamic routing protocol. It's what the functionality is. So we're going to talk about how that relates to OSPF as a dynamic protocol. First, I want to talk about different definitions so that you guys can increase your vocabulary as it relates to dynamic routing protocols. The first thing that I want to identify, or let me say define, is what an autonomous system is, or AS. It's a routing domain. It's a collection of routers under a common administrative domain, like an internal company network or service provider's network. And because the internet itself is based on the concept of the autonomous system, there's two different types of routing protocols that are required, IGP and EGP. So an IGP stands for Interior Gateway Protocol. It's a protocol that's used to exchange information inside of the autonomous system. An example would be EIGRP, RIP, or what we're going to talk about today, OSPF. An exterior gateway protocol would be a protocol that operates outside of an autonomous system. BGP, or Border Gateway Protocol, is the de facto standards for your service providers out there, and they utilize BGP to move packets between autonomous systems. So autonomous system is, again, all of the routers that are under a common administrative domain. So it's all of the routers that your company owns, for example, and is responsible for. And service providers will utilize Border Gateway Protocol to move packets from one company's autonomous system to another company's autonomous system. Now, within an autonomous system, your interior gateway routing protocols can be classified as either distance vector or link state. Let's talk about the two. The distance vector routing protocol determines the direction or vector and the distance, like hop count, to any other link in the network. So distance vector routing protocols like RIP don't have an actual map of the network topology. EIGRP, on the other hand, is an example of what we call an advanced distance vector routing protocol because it has some additional functionality. The link state approach, which uses the shortest path first, that's where we get open shortest path first with regard to OSPF, creates an exact topology of the entire network. I call it a soft copy of the network. And a link state routing protocol is like having a complete map of the topology. And it uses link state information to create that map in order to identify the best path to all of the destination networks in the autonomous system. And we're going to learn more about that link state routing protocol, specifically OSPF. A couple of other terms that I want to make sure that you guys are familiar with include classful and classless. And they refer to different features of different routing protocols. Now, these features can't be enabled or disabled. They either are classful or classless. Let's take classless number one. The classless routing protocol approach advertises the subnet mask information for each subnet, giving a classless protocol the ability to support DLSM as an example, which we talked about the other day. Classful routing protocols do not advertise the subnet mask. Therefore, they do not support variable length subnet masks. Okay? So that's basically it. Classless routing protocols do send the subnet mask along with their updates. Classful routing protocols do not send the subnet mask along with their updates. Questions? All right, now we talked about the two basic types of routing protocols being distance vector and link state. OSPF is an example of a link state routing protocol. So when there's a failure in your network, the routing protocol should be able to detect that failure as quickly as possible. Only link state routing protocols like OSPF support fast convergence with support for scalability in a multi-vendor environment. So it's the only interior gateway routing protocol that is found in a large network environment. So let's talk about some of the characteristics. Here it says that it's more scalable. It's designed in a hierarchy of very large networks when properly designed. Each router has a full map of the topology. So because each router contains all of the information about the routers and the links in the network, it's also able to select a loop-free and efficient path to every network that's attached to an interface on every router in the autonomous system. Updates are sent out when there's a change in the topology, meaning there's a link that comes up or a link that goes down, and they're reflooded periodically. So they have the ability to respond very quickly to changes in that topology. We call that a triggered update, as you'll see on the next slide. There's also more information communicated between the routers. So because they all have a common view of the network, they all have all of the information about all of the other routers, the links between them, including the metric on each link. So this slide identifies what happens after you configure OSPF on a router. Once you configure it, you discover the neighbors, then you form neighborships with those neighbors. You flood, it doesn't flood the link state database. This is actually incorrect. What it does do is it floods what's called LSAs, or link state advertisements, that are used to create the link state database. So that's not right. But then it computes the shortest path, and then those best path gets installed inside of the routing table. So that was a big introduction. Now let's introduce you specifically to OSPF. OSPF is a link state, as we said, routing protocol. You can think of a link as simply an interface on the router. The status of that link might be the description of that interface, including its relationship to its neighboring routers. It could include, for example, the IP of that interface, the subnet mask, the type of network it's connected to, the routers that are connected to that network, and so forth. And it's a collection of these link states that begins to form what ultimately is going to be created in the form of a link state database. Now, OSPF was developed based on an open standard, so it's supported by a number of router manufacturers. So it's often widely used as an interior gateway protocol, particularly in a large network environment. Originally, it was developed as a replacement for RIP. The advantage over RIP is its ability to converge fast as well as to scale to much larger networks. Now, a router configured for OSPF status. It also will send the metrics that are used and other variables that we'll talk about in a minute that are used to compute the cost of those links. And it's an accumulation of all of that link state information that's used by the shortest path first algorithm to calculate the shortest path to each network in the autonomous system that goes into the routing table. And as mentioned, the link state database is essentially a soft copy of the networks in relation to the routers. It's created using a collection of those link state advertisements that end up being sent out to all of the OSPF configured interfaces on all routers inside of the autonomous system. And because the routers in the same area contain the same information, they all end up creating an identical link state database. Now, OSPF operates within a hierarchy. The largest entity in that hierarchy is the autonomous system, which, again, we said is a collection of networks under a common administrative domain that share a common routing strategy. And as you can see here, as demonstrated, the autonomous system can be divided into several areas, which are basically groups of contiguous networks and their attached hosts. So here's an example of an OSPF hierarchy. It's a two-layer network hierarchy that has two primary elements. The autonomous system at the top, which we said is a collection of networks under a common administrative domain, and areas. An area is a grouping of contiguous routers and their attached networks. So areas are a logical subdivision of the autonomous system. It's an implementation of network segmentation. And then within each autonomous system, you start with area 0, which is called a backbone area. And then all the other non-backbone areas have to connect to the backbone area in some fashion. And that's what you see here on the slide. Any questions at all so far?
Yeah, what was the full AS the definition?
Sure. The autonomous system is a collection of all routers and their attached networks under a common administrative domain. So if you think about your company, Fabio, it's all of the routers that your company has responsibility for. If they're running OSPF, they would all be in the same autonomous system. Good question. Now, a multi-area design as an implementation of network segmentation is more effective since the network is segmented primarily with regard to OSPF to limit the propagation of those LSAs to a single area, which becomes more important as your network begins to scale or grow. But you also get the other benefits that we talked about. Isolating problems to a particular area, which is a benefit of network segmentation, being able to implement security policies more effectively, and to be able to manage and troubleshoot your network. All are benefits of network segmentation. Now, routers that are running OSPF have to recognize each other on the network before they can share information because they depend on the status of the links between them. And they utilize the hello protocol and the exchange of hello packets to create this adjacency. Now, there's some information that they need to agree on, and it's the information that is stored inside of the hello packet. And that would include the hello dead interval. They have to be in the same area. And if any authentication data is used, they've got to agree on that information there. Now, when you first configure a router for OSPF, the first thing that they do is send out the hello protocol. So before they send out the hello protocol, they're said to be in the down state because they haven't exchanged any information with any other router. Then they'll send out a hello packet through each of their interfaces that are participating in OSPF. Once they exchange information, the routers are said to be in the init state, short for initialization. So once they receive that hello packet, they'll send out a reply hello to the first router with its corresponding information. When that first router receives the hello from the neighbor, it'll add that router's ID to its hello packet in their own neighbor relationship database. Now they're said to be in the two-way state because now they're doing two-way communication. And then they're said to be in the exchange state where they begin to exchange information. So they'll send out what's called database discovery information, and they'll send out link state request packets. Hey, I need the entry for this particular subnet. They'll respond with a link state update information, and they'll send out a link state advertisement. And when all of those link state requests have been satisfied, then they're said to be in the actual full state. So after a router running OSPF recognizes other routers, what they do is they establish that neighborship with their directly connected neighbors by initiating that exchange of the hello packets. After they synchronize, after they establish the neighborship, they'll synchronize their link state databases by the exchange of those link state advertisements. And then after that database is built, they'll apply the shortest path first algorithm, and then the best routes to those networks is what gets installed as a routing table. These are the 5 packet types that are used: the hello packet, the database descriptor, the link state request, the link state update, and the link state acknowledgement packet. Now, the cost to reach a network is made up of the cumulative cost of all of the links from the source to the destination. So in our example, we're looking at the cost from router 1 to the network hanging off of router 4, which is a total of 40. So it's 10 to get to router 10 to get to router 4, and then 10 to get to the network off of router 4. So we're looking at a cost of 30. Cost to the router 3 LAN is 22, and a cost to the router 2 LAN is a total of 14. So we're looking at the cost. Now, the shortest path might not necessarily be the best path. Each router has its own view of the topology, even though the routers build the shortest path trees by using the same link state database. So here, again, we're looking at things from router 1's perspective. And a metric is an indication of the overhead required to send packets across an interface. And OSPF uses cost as its metric. So the smaller the cost, the better the path. So there's an inversely proportional relationship between bandwidth and the interface. So the more overhead or higher cost, the more time delays involved in crossing a 10 megabit per second link than crossing a 100 Mbps Ethernet link. So there's a formula that's used, which is cost equals reference bandwidth over interface bandwidth in bits per second. That's what OSPF uses to calculate costs. And just like the other protocols, we've got RIP next generation for IPv6, OSPF version 3, BGP4, and EIGRP for IP version 6. Questions, gentlemen?
So it sends the hello protocol or packets by itself. We don't have to do anything.
No, as soon as you configure what you're going to do in your lab, as soon as you configure a specific router or its attached interfaces to support OSPF, it will begin the process by sending out hellos out of each OSPF-enabled interface. Yes, correct. That is precisely correct. All right, so you're going to have an opportunity to configure and verify OSPF to give you a little more familiarity with it. So you're going to configure OSPF basically on router 1, and then you're going to verify the results. And this is the topology that you're actually going to be using. So let's write that down. That's going to be discovery number 16.
Yeah, I'm back.
All right, good to have you back with us. So that's discovery number 16. All right, let's get out of here. All right, I'm gonna suggest that we do this. Let's do another module, Ether channel. Then we'll go back and answer a few more questions since the mod's back with us. Then we'll break for the labs, and we'll combine the labs with our lunchtime break. How's that sound?
Sounds good.
Cool. improving redundant switch topologies with Ether channel. Anybody heard of the term Ether channel before? Anybody work with it? Know what it is? Who asked me about the redundant links on the enterprise architecture model on Monday? Somebody asked me about that. Was it Amat? Was it you, Fabio?
Yeah. I think that was Amat.
Oh, okay. We're going to talk about that now. This is where we're going to talk about that. All right? I think my machine was overheating because I forgot to turn my fan on. That's why it was slowing down earlier. That was my fault. All right. Let's talk about that. All right. So with the proliferation of bandwidth intensive applications, things like voice, things like video, interactive messaging, comes a need for greater network speed and scalable bandwidth.
Sounds like you're rebelling again.
How now I sound? Can you guys hear me?
Yeah, it still kind of sounds the same.
Still breaking up?
Yeah.
All right, hang on for a minute. On out. There you go. There.
In the portal, but nothing comes through until a few seconds later.
Huh. Hang on. You guys still having difficulty hearing me?
That sounds a lot better.
Okay. All right, let me know if you still have an issue. You can increase network speed by using faster links, but that's expensive. You can also increase network speeds by using more physical links. That's the doubling of the links that you guys saw. However, one of the downsides of that is that you've got to be consistent with your configuration. The second one is that spanning tree is going to block one of those links. So Ether channel is simply Cisco's methodology of increasing speed between switches by grouping several fast Ethernet or gigabit Ethernet ports into one logical Ether channel link, as you see in this particular slide. As a result, spanning tree doesn't search out to block one of the physical links to prevent a loop. And because all of the physical links in the Ether channel are active, you increase your bandwidth. So Ether channel is basically a marketing term from Cisco. It's Cisco's port aggregation technology. So this port aggregation technology can help provide more redundancy, because if you've got a link that fails, the device will fail over to another adapter to maintain connectivity. So, as an example, if you happen to lose one of the links here, then it'll fail over to the other links that are here, and you don't lose your connection. And it just looks like one logical link to spanning tree, so it doesn't try to block it. That's all Ether channel is. It's port aggregation technology to increase your throughput and your bandwidth without having to go out there and buy new equipment, because those are links that you already have. So this, for example, is your physical view. And when you create an Ether channel, what you're doing is you're bundling those multiple links so that it looks like one logical link to increase your throughput and to have failover in the event that you lose one or more of your links. So you can group from 2 to 8 physical ports into an Ether channel, but you can't mix the port types. So for example, you could group 4 fast Ethernet ports, but you couldn't have 2 fast Ethernet ports and 2 gigabit Ethernet ports. They all have to be the same. Also, all of your ports have to have the same speed, the same duplex, the same VLAN configuration, the same allowed VLANs, and they should be either trunk links or access links, not a mixture of both. So they're either going to be all access links or all trunk links. You could also configure more than one Ether channel between 2 devices. So you can have 2 Ether channel links creating one Ether channel and another 2 Ether channel links creating another channel. But you have to take into consideration that if spanning tree sees more than one link to the same location, the same switch, it will try to go out there and block it. Now, there's 2 ways to create an Ether channel. One is statically, or what we call manual configuration mode, with the on channel. So in this mode, the interface will be part of the Ether channel. You can also put it in passive mode, where it's passively waiting for the other side to initiate the negotiation of an Ether channel, or active, where it's actively asking if or will the other side will participate in an Ether channel. So LACP creates that Ether channel by detecting the configuration of each side and making sure that it's compatible so that it can establish an Ether channel link. So this table shows the various settings for LACP. Now, a layer 2 ether channel is seen as a single link by spanning tree so that you can utilize all of the members that make up that link for better performance. And most of the time, a layer 2 ether channel is configured as a trunk link so you can carry, of course, the traffic of multiple VLANs. A layer 3 ether channel is like a single port configured in routed mode with no switch port, so there's no VLANs here. And before you configure the port channel interface, again, you need to make sure that all of your interfaces have the exact same configuration. Because once you utilize that channel group command when configuring your ether channel, all of the interfaces will automatically inherit the settings from your physical interface. So here's your configuring ether channel example, where number 1, you're going to use your range command, and here we're going to use gigabit 01 through 04. You're going to create your channel group 1 mode active, which utilizes LACP. You're going to configure your port channel interface. You're going to specify that port channel as being a trunk. You're going to allow VLANs 1, 2, and 20. And you're going to apply that to all 5 gigabit Ethernet ports. And then you're going to enable it with the no shut command. Same thing if you're creating a layer 2 ether channel. You've got to manually create the port channel interface and then put your ports into the ether channel group. So this is a configuration step that you're showing here. Once you've configured your ether channel, there's a number of show commands that you can utilize to verify that you've configured it correctly. If you look at the output of the show interface port channel command, you can see that your port channel is up, your protocol is up. So again, layer 1 and layer 2 are functioning properly. That show ether channel summary can also be used to display one line of information per port channel. So here we can learn from the last line that group 1 is using LACP. This is a layer 2 ether channel symbolized by the SU, where the S means layer 2 and the U means that the port channel is up. You can also look at the output of the show ether channel port channel command. We can see that we're using LACP as the protocol. We're using FA01 and 02 as part of this ether channel. So in Discovery 17, you're going to have an opportunity to configure and verify ether channel. So this will give you some experience working with ether channel. Notice that you've got pairs of connections between your switches. However, just because you've got pairs of connections between the switches, it does not automatically lead to doubling the bandwidth by default. That's where you're going to configure ether channel on some of the links, and then you're going to look at how it impacts your throughput. Any questions on this particular lab number 17? Any questions, gentlemen?
What's the range command?
The range command, good question. The range command allows you to make configuration changes to one device, but apply it to a range of devices. So for example, this is the range command. So I'm saying I want to make the following changes to gigabit 0, 1, 2, 3, and 4. So all 4 of those devices are going to get the same commands, the same allowed trunks, the same port channel 1, the same channel group 1 mode active. So that's so that you don't have to issue the same exact commands more than once. You can use the range command, and it will apply that configuration to all 4 interfaces. Good question. Any other questions? All right, let's do this. Let's answer some more questions now that we've got Amat back. $29. That's what I wanted. $29. All right, we did in fact answer this one. I'm going to skip that one. All right, Amat, you with us? Yes. Okay, fantastic. All right, host A has established a communication session with Bravo for the first time. The question asks, what enabled router 2 to forward this traffic in the appropriate direction to reach the network to which host Bravo is attached?
A routing protocol?
Yes, a routing protocol. Excellent. So you really have to answer, how do those routes get in the routing table, right? The only thing that gets it in there from this list is a routing protocol. Excellent. Excellent by you. All right, what actions must a router take in order to route incoming packets?
I'm going to go grab a water bottle real quick.
No problem. Do we need 5? Amat, you want to take 5? All right, let's take 5. We'll be back in 5 minutes.